All right, I think we can get started. Hi, everyone. Welcome back to the workshop on safe robot control with learned motion and environment models. So we are starting our afternoon session, depending on which time zone you're in. I guess it is for us at least. So we are going to have two talks and then some interactive session with the with the paper presentations we saw in the morning. But before that, we have two really exciting talks. So the first one is by Dr. Rose Yu. Dr. Rose is an assistant professor at UC San Diego in the Department of Computer Science and Engineering. She's also affiliated with the Data Science Institute. And Dr. Yu's research focuses on machine learning, and especially for large-scale environmental spatiotemporal data applied to both environmental monitoring, but also dynamics learning. And today she's going to talk about incorporating symmetry in deep dynamics learning. So Rose.
Thank you. Thank you, Nikolai, for the invitation, and thanks for organizing this wonderful workshop. So I direct the Spatial Temporal Machine Learning Lab, and this is the logo of my lab. If you stare at it for a few seconds, you might have already recognize the word S and T in this little logo, and that stands for Spatial Temporal, and there's a rose in it, so that's just my English name. So I wanted to talk a little bit about some recent work that we did in a group for learning dynamics model with deep learning. But let's start with a very simple example. Let's say we want to learn a very simple dynamics in the form of a sine function. So here we're looking at a sine function, and by learning dynamics, we wanted to do forecasting. So the model see the trajectories in the past on the left-hand side of this vertical line, and the goal is to predict the future points on the right hand of the vertical line. So this is an example from our recent paper in L4DC. Basically, if you think about the simple system, it's only governed by a few parameters, which is the magnitude of the sine function, the phase, which is the initial condition, as well as the frequency. And we can call these parameters together as a variable theta. What I wanted to highlight in this simple example is that if we have training set, let's say theta TR, it stands for training set parameters, and we basically generate a lot of data examples in this format from the training sets with parameters sampled from interval A and B. And then during the test, we can draw some other examples with the similar type of dynamics data on the test, which is theta TE, also from the interval A and B. But of course, we don't want the test set to be similar with the training set, so the examples are different, right? But only the parameters that govern the dynamics are drawn from the same distribution, which is the interval between A and B. And if you look at the prediction of a deep learning model, here we're testing with the sequence-to-sequence model. You can see that the prediction of the sequence model overlaps perfectly with the ground truth in the forecasting setting. So that's not surprising, because we know deep learning models are universal functional approximator. Now let's look at a slightly different setup. Let's say we have a same dynamics function where the training parameters of this dynamic still comes from the interval A and B, uniformly sampled. Now, the test set parameter theta TE is coming from a different distribution, where the parameters, which in this case is the initial condition, the frequency, and the magnitude of the sine curves, are drawn from a different interval, let's say B and C. Now, if we look at the predictions of this deep learning model from a sequence-to-sequence architecture, the predictions are completely off. And in fact, we tried most of the state-of-art deep learning models for dynamic forecasting, and all of them failed in this case. So that basically point out to a fundamental challenge in learning dynamics, which is generalization. So in the traditional machine learning sense of generalization is basically about the same intervals, but different data sets, right? We're not talking about distributions that are coming from completely different dynamics. And on the right example here, even though the data distribution roughly follow the same range from training to test, the dynamics that governs this data have changed significantly. And that's what we mean, the generalization challenge for dynamics learning. And what we found is that deep learning models struggle with changing dynamics, and which is a very critical issue in robotics and automation, because when we train our robots on certain dynamics and we want to test it on an unknown environment, it's very likely that the dynamics will change. So if we use a deep learning model, no matter how powerful it is, it's going to suffer from the changing dynamics problem. And that is very critical for the safety concern in this context. So in this case, right, we know that the performance degrades significantly with test distributional shift. So I want to mention that this distributional shift is not in terms of distributional shift of values, let's say the values of the sign function, but rather the distribution of the parameters that govern the dynamics. So what can we do to address this problem? This idea behind this talk is that we can probably leverage the fact, even though the dynamics have changed from training to test, the law of physics do not change from training to test. And that's a key insight that we use in the recent papers that we publish about utilizing symmetry to improve generalization for learning dynamics. And there's this beautiful theorem from Noether, who is a physicist, and she said for every symmetry, there is a corresponding conservation law. So this theorem essentially links the idea behind symmetry with the idea of physics laws, right? Because, for example, translational symmetry will correspond to conservation of momentum. Time invariance will correspond to conservation of energy. So if we can build in symmetries into deep learning models, then automatically we can guarantee the models knows about physics and therefore can generalize to unknown dynamics, even the dynamics are changing from training to test. Another benefit of doing so is that physics in some ways encode our knowledge of the physical world, including the robots. So by incorporating symmetries into deep learning, we also introduce inductive biases into the machine learning model. And from learning theory, we know that introducing inductive bias can also reduce the sample complexity, which means we will need far fewer data points to learn in very complex environment. Okay, so that's the high-level pitch of this talk. And following, I'm going to give two examples to demonstrate how we can leverage symmetry to improve the dynamics learning. The first one is about turbulence forecasting, right? So this is a very challenging task. And the idea is to take the past frames of the video like this and generate the future frames. So we know turbulence are governed by nonlinear dynamics, such as Navier-Stokes equations, and it's impossible to forecast for long term, but it is still possible to forecast for short term, where the ultimate goal is to develop a deep learning model that can predict much faster than the conventional numerical solvers. So this work was published at ICRA, led by my PhD student and postdoc Robin. So let's maybe review quickly some basic knowledge in group theory. A group theory is essentially the principled methods to describe a symmetry in our physical world. So by definition, a group is just a set. It has a composition map, which maps the two groups into the third group. So identity is the element in the set. For every element in the set G, we have an inverse operator, G inverse. So if a set that satisfies these conditions, it will become a group. A familiar example of a group is the rotation group in 2D, and that's SO2 group. And it's obvious that identity is a set is the element in this group. And for every left rotation, we can have the inverse operation of right rotation. So what we mean by symmetry is essentially a property defined based on a group. A group is invariant if we have a function f and a group G, whereas when we apply a transformation to the input, which is g of x, and it will not change the output of this function, right? So f of g of x is the same fg of x. So applying this group transformation will not change the output of this function. And that's what we mean by G invariant. A more general notion of invariance is equivariance. It's easy to see that invariance is just a special case of equivariance, which means if I have a function f and then I have a group transformation G, when I apply a transformation to this input, it will automatically apply to the output of this function. So we can basically alternate the orders from f and g. So f of g of x will equal to g of f. Let's look at a simple example. Let's say this function is a velocity field over the space x. So f of x with a v, when we scale it up, it represents a function that scales the magnitude of the velocity field by 2. Let's consider the group as a rotation group. So you notice this little notation row here. This just represents, it's a representation of the group, which is essentially a matrix. It's a matrix representation of this rotation group, which is basically a 2x2 matrix with elements cosine, sine, minus cosine signs in it. So what we mean by G equivariant is saying that, let's say I have a velocity field in this left top picture, and I apply a functional transformation to it, and by scaling the velocity field by 2, so you can see that the little vectors basically get scaled up by 2. And after that, I rotate the vector field by 45 degrees, and that will reach to this final picture on the bottom right. So that basically completes the loop of f of g of x, right? And by definition of G equivariant, we're saying if we rotate this velocity field first, right, by 45 degrees, and then scale it up by 2, it basically have the same effect. So f of g of x is the same as g of x. And that's the definition of G equivariant. So the reason we wanted to leverage equivariance in this context is that if we apply, let's say in the training, in the testing, some group transformations to the data, right, this transformation will automatically generalize to the output of the neural network. So that means even though to a regular neural network, it will not recognize this change in the distribution, for equivariant neural networks, it will automatically detect this change in distributional shift and being able to generalize. Okay, so in this context, we're working with turbulence, right? And that basically point out to the symmetries of differential systems. So a differential system is just a set of operators, right? And by definition, if we say the differential system have a symmetry, that just means if, let's say, a phi is a solution of this differential operator, then a group transformed phi is also a solution of this differential operator. So by this definition, we can pretty much list all the symmetries that different differential systems satisfy. So for instance, we can look at the Navier-Stokes equation. Right? Navier-Stokes equation are the governing equations of turbulence. And by basically plugging in different group transformation of the solution, we can prove that, well, if not we prove, we can just show that this Navier-Stokes equation satisfies different type of symmetries, such as space translation symmetry, uniform motion symmetry, scaling symmetry, etc. So the next step in building symmetry into deep learning is to design deep learning models that are basically intrinsically equivariant. So that points us to the relatively new topics in machine learning about equivariant neural networks. So when we say a neural network is equivariant, we just meant that this function that is approximated by a neural network is G equivariant, right? So we're approximating this function G or F with a neural network. And if we think about the simplest neural network F here as a multi-layer perceptron, what we want is that if we apply a group transformation to the input of this neural network, this group transformation will automatically apply to the output of the neural network. So for any neural network, the input and output representation are fixed because that's our feature representation and the prediction that we want. We can't do anything about it, but we can do a lot of things in between, which is to define the intermediate representations of this neural network. If we can guarantee that each layer of this representation is G equivariant, then this entire neural network is equivariant. So in our paper, we proved that this is just a simple proposition that says if every layer is equivariant, then the entire neural network is equivariant. Even in the presence of residuals like skip connection, it does not change the equivariance property of this construct. So how can we implement in practice? And there is a very well-known result recently published by Weiler and Sisa, which gives the sufficient and necessary condition for building equivariant neural networks. Essentially, if in a convolutional architecture that the convolutional kernel satisfies the group invariance under conjugation, which is applying a matrix operation with respect to this group, and right multiplied by the same matrix representation for the group, if the kernel satisfies this condition, which in group theory is called group invariance under conjugation, then this convolutional layer is G equivariant or group equivariant. So the simplest example we know is convolutional neural network, and that's just a special case of this theorem, right? Because convolutional neural networks satisfy translational invariance, and it just automatically satisfies this condition under translation symmetry. So in this paper, we developed the different group equivariant architectures based on this general condition. In essence, we can design convolutional architectures that are rotational equivariant by constructing the matrix operator of this rotation group, the uniform motion, which is basically by conjugating the model with shifted input distribution, and scale equivariance, which essentially try to design kernels that can satisfy scale equivariance. So for physical dynamics considered here, which is to forecast the evolution of turbulence, there's a little bit of nuance here. Because for physical dynamics, we not only need to consider the scaling in terms of resolution, because we are essentially forecasting a video frames into the future, and the resolution of the frames matter. So that's the image resolution, which we can compute using, again, the shifted input distribution by dividing the mean and multiply by standard deviation. So the second type of scale equivariance is the physical scale, and that's related to the differential equation themselves. So in this case, we need to generalize the idea of convolution and design the kernels that satisfy this group equivariant invariance property under conjugation. Okay, so with this new type of convolutional architecture that satisfies group equivariance, we can show that, let's say we want to forecast the evolution of Rayleigh-Bernard convection, which is a type of turbulence. And when we train our model on a certain dynamics, and we want to test our model on a very different dynamics, where we change the tested distribution of the data by either rotating it or scaling or doing a different type of transformation. To a non-equivariant model, these test distribution data will look completely different. So the models will fail with the same reason as I showed before in the first slide of this talk. However, for equivariant models, because it can automatically identify the group transformation that has been applied to the input, it will automatically apply this transformation to the output, and hence they will be able to generalize. Let me show you some examples. Let's consider rotation. What you see here, the left is the target, which is the ground truth, and then the middle one is the prediction from a non-equivariant model. Even though it's one of state of the art for video forecasting, it completely fails with changing dynamics, whereas the equivariant model predicted well in this case. And this type of property holds for different type of group transformation, such as uniform motion and scaling. We also evaluated this method on the real-world ocean current forecasting dataset. And in this case, we're scaling the test data by different factors. And that's on the x-axis, where we upscale the dynamics by different factor 1 over lambda. And we're measuring the mean square error and the energy spectra of the forecasted velocity field, compared with the equivariant model in blue and the non-equivariant model in gray. So we can see that as we scale the test set by different factors, the non-equivariant model, in this case the ResNet, completely fails with exploding error, not only in terms of forecasting root mean square error, but also the physical quantities in terms of energy spectra. Whereas the equivariant models that we develop in this case is relatively robust against this kind of group transformation. And as a second example, we also test this idea to a real-world application of forecasting trajectories for autonomous vehicles. So in the previous work, we discussed an idea of applying symmetry from differential systems to generate better forecasts for turbulence. But for physical systems such as fluid dynamics, we have basically equations that govern them. So in real world, such as this kind of complex vehicle trajectories, there's very little equation that we can write that can govern the dynamics of the system. So it's a much more complicated task from simulation to real data. And on top of modeling the complex dynamics, another challenging factor is the human psychology. So we have to also model the human behavior behind the data in real world. And in doing so, we also developed a new type of method of incorporating symmetry into deep learning to forecast the real world trajectories. And this work led by my postdoc, Robin, and grad student, Leo. And was published also at ICRA. So our model is built on the key insight that for autonomous vehicles or vehicle trajectories, we can think of them as many particle systems. So many particle systems pertain intricate internal symmetry. Let's consider this example where we want to forecast the trajectory of the cars on the road. So this little dot with a tail on it represents a vehicle. So on the left side, we're looking at the intersection where we wanted to model to predict a right turn. So if a model is successful, then it should be able to distinguish left from right turns. So if we rotate this reference frame by 90 degrees, then the model should give consistent predictions. Even the reference frames or this intersection has been rotated with slightly different orientation. So that's the key insight that we use to develop the model in this paper, which basically incorporate rotation symmetry in these many particle systems. And what we want is the model can give consistent predictions with different orientation. I also want to mention that in many of the existing trajectory prediction work, what people do normally is just to normalize the data frame by frame and rotate everything to the same orientation. And this works for a single agent prediction, which you can basically define the reference frame and rotate the seam accordingly. But it's impossible to do that if we want to predict for multiple agents at the same time, because we don't have the unique reference frame anymore. So that's basically the bottleneck. If we opt for the simple trick to rotate the seam and normalize the data in the beginning of training. Now, our method, however, does not require this type of normalization. The key idea behind this work is built on top of continuous convolution. So continuous convolution is essentially a generalization of graph neural networks. So we have developed previous works to model graphs and model dynamics on the graph using graph neural network, right? Essentially, we compute this type of irregular convolution on the graph with a certain type of graph convolution. And this is on a discrete convolution, right? Because the graph is fixed, and we only need to define an adjacency matrix A and compute some function across some functional operation on this adjacency matrix A. So in the case of point cloud data observed in autonomous vehicles, we do not have a fixed graph anymore. Instead, the position of these cars are changing all the time. So we build on the previous work of continuous convolution. So essentially, for every point, in the case of I, right, we define an xi, we need to compute the changing neighbors of this position I, and then convolve around this neighbor in this pink circle as a convolution k applied to every neighbor j that is inside the circle. And f of j is the feature, which is the position of the cars within the local neighborhood. However, continuous convolution itself is not equivariant. The key contribution of this work is to generalize continuous convolution and make it equivariant. And basically, we can use the same idea of weight sharing to design continuous convolutional operators that are equivariant under continuous rotation. So what we did is to define this kind of kernel, k of theta and phi, and over the polar coordinates, where the first entry is the angle, the second entry is the radius. Based on the general principle that this kernel, k, should be a group equivariant under conjugation, basically we need the group kernel to satisfy this condition, where we have the rotation matrix on the left and the inverse of this group operator on the right-hand side. So in weight sharing, what we ended up with is this type of polar coordinate. For every vehicle that we are focusing on, we define a local neighborhoods, and then within this red sectors, the weights are different and they're freely trainable. But for every circle along this radius, the weights are shared. But they're shared, but according to a circular shifting rule, because they're rotated with certain patterns. As you can see here, for every little, like I call it pizza slices, we have a tiny matrix, which is this kernel at 0 angle and r radius. So we rotate the parameters of this kernel along the radius and only correspond to the shifting rule of the matrix entries. Along these red sectors, the weights are freely trainable. The only caveat here is we have to be careful with this both I. So this is a singularity point in this polar coordinate. We need to constrain it to be circular so that this also satisfies group equivariance that we want. It turns out that this kind of circular pattern that we defined for the kernel basically corresponding to functions on the circle. So it became a torus kernel. Right? Essentially, this tiny matrix here, when we fold it up along the angles, it's become a torus. And anytime when we cut it open around this particular angle, it will unfold into a band, and that is correspond to the ring. And then this tiny matrix is this matrix corresponding to the position. That's the matrix field of this position. So that's some interesting geometric interpretation of what we're constructing here for the torus kernel. So essentially, we designed a new type of continuous convolution that are guaranteed to be equivariant under continuous rotation, right? What we did is that we can use this continuous convolutional kernel as the basic modules in our prediction framework. So we use an encoder-decoder type of architecture to predict the future positions of cars. Essentially, we have an encoder that encode the past of the trajectories. So we have separated three different components to encode, for example, the map information in the autonomous vehicle, the interactions between different agents, and the single agent according to this past. So for each of the components, we use continuous convolution to encode the past, and we decode the future to generate the predictions. Instead of predicting the absolute position of the cars, we're only predicting the increment with delta x, and we added the increment to the original position to compute the position of the next timestamp. So for the decoding part, we also use our continuous convolution with Torus kernel to predict the future positions. So if we look at the performance, when we compare our model, which is ECCO, with slightly different variations, we can see that our model are much more accurate on the benchmark data set for Argoverse and TrajectoryNet. More importantly, because we're incorporating inductive biases into our model, the number of parameters in our model are much smaller than baselines such as LTMs or continuous convolution, which is our main competitor, which demonstrates the benefit of incorporating symmetry in this case. So when we look at the number of examples we need to train this model versus the validation loss, we can see that the symmetry encoded neural networks that we built here trains much faster than the baselines. We can see this demonstrate that encoding the inductive bias of symmetry into deep neural network can significantly improve the sample complexity of the learned model. And that basically validates the idea of using symmetry as an inductive bias to reduce sample complexity. Okay, to conclude, I talked about incorporating symmetries into deep neural network for improved dynamics learning. And I gave two examples. One example is differential equations, which allows automatic generalization to dynamics of different group transformation. Talk about point cloud data, where we incorporate symmetry into continuous convolution to improve sample efficiency in autonomous vehicle prediction. In future work, we would like to incorporate uncertainty with probabilistic forecast. And I would like to acknowledge, oh, by the way, you can check out the source code and data on my website or follow me on Twitter. And I would like to thank the support from various funding agencies. Thank you.
Thank you very much, Rose. This was a really exciting talk. I think we'll take just one question because we're slightly behind schedule and move on. I see one question in the chat from Ty. So Ty is asking, are the results on G equivariance similar to the theorem you showed apply to other kinds of networks like multi-layer perceptron? And what if the input is not an image?
That's a great question. So we have a new paper that's on arXiv, which extended G equivariance to more general architecture. There are actually several recent papers about G equivariance for graph neural networks, for recurrent neural networks, which doesn't have to limit to convolutional architecture. In terms of the image data, actually our data is not an image for the second example. Our data for the vehicle trajectory is just a point cloud, right? As I mentioned, if we're working with graph neural networks, the data can be completely irregular. And for like recurrent neural network type architecture, the data can be sequential.